about to prove the third one. First,
2 o'clock.
just to remind you that if the power of P divided the order of the group, then there existed another group H, which was a subgroup of G, and the order of H was P to the R. Yeah, that was the first one. So for every power of a prime that divides the order of the group, there does exist a subgroup of that particular size. We then defined Sylow P subgroup, HJ Sylow P subgroup. That meant if H is a P subgroup, so it consists of elements whose order is a power of the prime P, and also H maximal. Now, maximal, as kind of Jan pointed out to me, clarified. I mean, it'll turn out that maximal means, I was remembering that, that the size of H, it'll turn out the size of a Sylow P subgroup will be the maximum power of P that divides into G. But the definition itself doesn't explicitly say that. It just says H is a P subgroup, so its order is some power of P, and that it's maximal. That means it's not contained in a larger P subgroup. Yeah. So it's maximal in the inclusion sense. It's the biggest such thing. What do you laugh? You're making me paranoid now.
You mispronounced P, but you instead accidentally walked into a series of in-jokes from a series we watched.
Okay.
Okay, Grumps. Very sorry.
Okay.
I'm very tempted.
No worries. So does everybody understand that maximal notion?
Yeah.
That it is a P subgroup. In the number theory, I'm talking about P minus 1. But anyway, maximal. So there's no bigger subgroup containing H that is also a P subgroup. The second theorem, second Sylow theorem, which we proved yesterday, proved that all the Sylow P subgroups are conjugate to one another. Okay, so given H and K, two Sylow P subgroups, you can find an element from the group such that if you conjugate H, you get K. Okay, they're all conjugate to one another. This relation of that might hold among subgroups of being conjugate to one another, it's an equivalence relation. So it's going to be symmetric, transitive. As a consequence of that, as a corollary of that, you could say here is from that, proof of this doesn't assume that all the Sylow P subgroups have the same size. But we get out of it a corollary now that they do. So H and K are Sylow P subgroups. Then the size of H is the size of K. And so it must be this maximum P to the R, such that P to the R divides G, but P to the R plus 1 does not divide G. So it's the maximum power of P that divides into G. Does that make sense? The first theorem says there will be a P subgroup of that maximal size. If it's the maximum size, it clearly must be Sylow. It can't be anything else containing it. But now, because they're all conjugate, we get as a corollary to that they all must have the same size. And the reason is that the proof of that is that conjugation, which is a map from H to K, is 1-to-1. It's 1-to-1 and onto. Yeah. So it shows that they have the same size. And onto. Biject. So the two subsets of the same size. So, okay, so any questions on the review? So now we come on to the third theorem, which you, Jordan, led us into naturally with your question last time. So because you asked, well, okay, well, how many of these things are there? Well, know, there's no simple universal answer to that, but we get the third theorem gives us excellent conditions on the number of them. So the count, let's call it M, of Sylow P subgroups, the number of them that there are, satisfies two conditions. M is congruent to 1 modulo P, and M is also a divisor of the size of G. So that's very strong restrictions on the possibilities for the number of these Sylow P subgroups. And in a lot of cases, well, in some cases, when you're looking at a G of a certain size, this will be enough information to say, just from the size of G and the prime divisor that you're considering, these two conditions will be enough to pin down exactly the value of them, exactly to say how many of these are. Okay. So we haven't proved this third one yet. So this is the proof of it now. Well, it's but well, that's it. Proof again, it just brings in this notion of action by conjugation. It's amazing. It comes in many forms in these proofs and in dilemmas that we're leading to them. It's lots of different instances of this action by conjugation, both on the elements of G and also on systems of subgroups of G. Okay. So it shows how powerful an idea it is. Remember, we heavily focus on the class equation to get the proof of the first theorem. The central idea, looking at the properties of the terms in the class equation and their divisibility or not, allowed us to draw conclusions ultimately about the existence of the subgroup. So now for the proof of the third. So we let P be a Sylow P subgroup.
And I want to show right out what I was going to talk to. Let's just talk to him. If I have think of something to add, I'll add it on the board. Okay.
So what kind of action? Well, we're going to look at an action by conjugation on a system of subgroups of G. Which system? Well, we're going to choose a Sylow P subgroup. And we're going to let it act on the set of all Sylow P subgroups. So curly S is all of the Sylow P subgroups that there are. Okay. So K, the K mentioned here is actually this M. The count K. It's another notation agrees. So these are all the Sylow P subgroups that there are. Okay. And we're going to name the first one P1. We're going to name that P. You can call it P1 though, because he wants to keep referring to it. He's just going to call it plain P. So P is the first one, and there may be others. And we're going to consider the action of the elements of P on this system of subgroups by conjugation. So we're going to consider conjugates of one of the Sylow P subgroups by an element little p. Ooh, no, I won't do that. I criticize people for using little p for elements because it's already in use for primes. So I'm going to take an x. We're going to look at these conjugates, but not taking any old x from the set G, taking x from this nominated Sylow P subgroup. Okay. So the elements of that will act on the Sylow P subgroups. It conjugates them. Conjugate of a subgroup is always another subgroup. Yeah. And it will be another subgroup because the size of the conjugate will be the size of Pj. We know, but that will again be of maximal size, so it'll again be a Sylow P subgroup. Okay. So the conjugating by elements from P is an action on this set. Takes one of these subgroups and gives you maybe another one, maybe the same subgroup again, or one of the others. It never pops you outside of this set curly. So it is a legitimate action on curly S. Now, okay, P is one of the sets here, yeah? And it's clear, it's always the case that for every X in P, if you conjugate P itself, in other words, P1, conjugate P itself by X inverse, that's always just going to be a rearrangement of the elements of P. Yeah. So this is what it's saying here. The only P conjugate of P is itself. That's what it's saying here. That's what he's emphasizing here. Yeah. So if you look at the orbit of P, that's the general terminology from group actions, but the specific, that's the ocean. Specific terminology we use here is the conjugacy class. Conjugacy class of P, the orbit of P is the general term. The appropriate language here is the conjugacy class of P is simply just P itself. Yeah. Because you can't get anything else from conjugating P by elements from P. And that's mainly because of the closure property of subgroups. Subgroup is closed under multiplication, and you're just taking another element from P, multiplying elements from P by X, you're still in P, multiplied by the inverse of X, you're still in P. Can't get anywhere, so you're always going to just land back in P. So the conjugacy class of P1, namely P, is just P itself. How big is every other conjugacy class? So if you take J bigger than one of these J's, the conjugacy class of Pj equals what? Well, name me one thing that's in the conjugacy class of Pj. Pj itself. When you conjugate Pj by the identity, you just get Pj back. E, Pj, E inverse. That's just Pj. So certainly Pj is in. Yeah. Is there anything else in it? Well, maybe, maybe not. Does there have to be?
Depends on whether or not the element exists in Pj to begin with.
Yeah, okay. Valid point. If the X that you conjugate Pj by, if it's in, actually turns out to be in Pj to begin with, then it will just give you back Pj. So it won't give you something else. Remember, these are all different subgroups. So there must be at least a few things in Pj that are not in P. I mean, the E is the example of the intersection. The E is always in the intersection of any two subgroups. There might be more stuff. But because Pj is distinct from P1, there must be some other element. So it's what do those other elements do?
PK.
Well, PK is the last one.
Yeah.
So what we're asking ourselves is it possible, or must you always have an additional, at least an additional one? Well, it's actually in one of the lemmas we did before. It was one of the lemmas that fed into the proof of the second. You see, this condition here, okay, it's written X inverse Px, but it's essentially the same thing. Conjugating P by X, if it gives you back P, and in addition you know that X has order a power of P, then giving you back P means X in fact was an element of P to begin with. Okay? Now where are our X's coming from? They're coming from P, which is a Sylow P subgroup. It's a P subgroup. Every element in it has its order a power of P. So the X's that we're considering that are conjugating Pj, yeah, they qualify as being under the scope of this lemma because they do have order P, because they're coming from a P subgroup, Sylow P subgroup. So some of them might give you back Pj, such as the identity, E inverse Pj, E does give you back Pj. And yeah, the identity is in Pj. Pj is a subgroup. But any other element that gives you back P, it must be in Pj. So that means it can't be the case. So don't take this down, because I'm arguing proof by contradiction. It can't be the case that the conjugacy class of Pj is just Pj itself. Because that would mean every x conjugated Pj to Pj. That would force every x from P, namely P1, to also be in Pj. That would force P1 to be a subset of Pj. But it's not. It's a C-log P subgroup. It is not contained in any larger subgroup. Or it would force us to the conclusion that P1 is equal to Pj. Pj, remember, is one of the other P's here. But P1 can't be. This list is a listing of all the set of C-log P subgroups. So we're assuming these are all distinct. Yeah? So that's a little proof by contradiction that this conjugacy class cannot only consist of Pj. There must be at least one other P, right? Probably a few more. In fact, there must be a few more. If you also look at the arguments that we went through in the second Sylow theorem, we actually showed. So in the second Sylow theorem, we were conjugating. We had all the P's were all the Sylow P subgroups. No, we were looking at conjugates of P, conjugates of a Sylow P subgroup. And at one stage, we started conjugating them by elements from another Sylow P subgroup. We reached this conclusion: the number of conjugates in every equivalence class in the partition is a power of P. A power of P. Now, what did I just rule out with my little proof by contradiction? I ruled out that it can't be just one element here, namely P to the 0. So I ruled out the possibility of P to this. So there must be other elements in here. And in fact, the count of these, the count of those must be P to the alpha for some alpha strict greater than or equal to 1. It must be either P or P squared or P cubed, some power of P elements in here. But I'll go back to my lovely neat writing up here. For curly S, which is P1 through Pk, this is partitioned by the conjugacy class. By the conjugacy classes of the PIs, of all these P's. Yeah. Under this action, under conjugation by elements from P, it partitions S. Here's figuratively curly S, it's partitioned into cells. And we started off by proving that one of these cells is the cell that consists of P1 alone. Right? The size of this one is size 1. It only has one thing in it. But every other cell has multiple elements in it. They don't have to all be the same. Every other cell in this partition has size P to the alpha, where alpha is bigger than or equal to 1. Different alpha, potentially, in each case, right? But all the other sizes. Right? So K, which is the size of curly S, is the sum over the cells of this partition of the number in each cell. Right? So let's count them. So it's non-trivial power of P, non-trivial power of P, non-trivial power of P. Adding together a load of non-trivial powers of P just gives us some multiple A times P. What's the last one? So that proves that K is congruent to 1 multiple. Right? Now the structure there is quite your A is quite complicated. It's a because the count is some power of P plus some power of P plus some power of P. But all these powers of P are non-trivial. They're all at least P. So you can extract out of each of them a factor of P. Yeah. But then there's this one special conjugacy class which consists of just P1 itself. This is the one that's doing the conjugating. Yeah. We're taking the x's from here and doing the conjugating, and it's on its own. So these conjugacy classes, they partition this set. So the K is the count of the things in this set. So some product, some multiple of P plus, so it's congruent to P. Congruent to one multiple. Makes sense? Okay. So that's the first conclusion. The K is congruent to one modulo P. The second conclusion is to, again, switch around the action a little bit, still acting on the set curly S, but now not restricting the conjugating elements, now allowing them to come from G. G conjugates of the Sylow P subgroups, right? But the second Sylow theorem told us, I've rubbed it out, that all the Sylow P subgroups are conjugate to one another. Yeah. So there's just one conjugacy class, one orbit, consisting of all of the things. Yeah. Because they're all conjugate, you're allowed to conjugate by any element from G. Now suppose G acts on curly F's by conjugation. Since all Sylow P subgroups are conjugate from the second Sylow theorem, there can only be one orbit under this action, right? So just pick out any one of them, the orbit of any one of them, the orbit of P1 is all of them. And from the previous chapter on group actions, we know the size of an orbit is the index of the stabilizer of that element. Specific language here, stabilizers are called normalizers. So it's NP. So this is K. K is the size of S. It's the index in G of a certain subgroup. So that means it's, what's the index in G of a certain subgroup? It's the size of G divided by the size of that. So what you're left with is a factor of G. You're taking G and dividing it out by maybe some of its factors, but the result is a factor of G. So K is a factor of G. So that's the second one. K divides the order of G. Yeah. GNP is a divisor of G, consequently the number of Sylow P subgroups from group must be. So that's it. So it's really making maximum, it's really nice. It's to maximum effect. It's applying this technique or this tool of group actions all over the place, and it's switching all the time. It's confusing. Sometimes we're conjugating elements by elements. Other times we're conjugating subgroups by elements. Sometimes we're restricting the source of the conjugating elements. Yeah. Which kind of different selections from the overall, conjugating subgroups by any element from G or restricting the selection of elements from G. But these conditions, so there's no universal simple answer. There are K Sylow P subgroups and K equals some simple formula depending on G or whatever. But we get this restrictive information, restricts the possibilities of K. And it's quite powerful. And in many instances, it allows you to say exactly what K is. So let's look through some of the examples here. Yeah, so our first one, A5, our favorite one, A5. So A5 was the one when we looked at the definition of normal subgroups. That was the one we proved that A5 was, well, no, it was first after considering Lagrange's theorem. A5 has no subgroup of order 6. Thank you. The size of A5 was what?
or 60. 5 factorial is 120. So A5 is size 60. And it had no subgroup of half the size, was it?
Is it not something to do with like the alternating group class A5 is simple or is not simple? I can't remember which way around it was.
Oh, maybe it was. Maybe I'm misremembering.
Because I think it's A4 that has no subgroup.
Ah, it's A4. Yeah, A4 is size 12. Sorry, A4 is size 12, but it has no subgroup of size 6. So, sorry. Okay, A5. Ah, yes, I think we're about to prove it does have a normal subgroup. Oh no, A5 has no normal subgroups.
Maybe it's
This is
beyond A5.
That was, yeah, I think that was pretty good. Yeah.
Well, but let's see what it says, okay? So A5 is size 60. So the factors of 60 are 2, 3, well, the prime factors are 2, 3, and 5. 60 is 4 by 3 by 5. So 2 squared, 3, 5. So what are the consequences then for the number of the various Sylow P subgroups that A5 might have? The sides of A5 is 60, which is 2 squared by 3 by 5. So it has Sylow P subgroups. Sylow 2 subgroups. Well, I'll put subgroup or groups for debate or for examination, many they have, but they have order 4. Yeah. And it has Sylow 3 subgroups of order 3 and 5 subgroups of order 5. Yeah. So it's the largest power of that prime dividing the order 2. How many of these things does it have? Like the count of each of them, well, let's call that K2, let's say K3. I'm going to call them K1, K2, K3, but maybe more natural to have the index be the prime. Yeah. So K2 is the number of count of how many 2 subgroups there are. K3 is the number of count of how many 3 subgroups. So can we work it out? So K2 must be congruent to 1 modulo 2. And K2 must divide 60. Yeah. So congruent to 1 mod 2 means it's an odd number, i.e. K2 odd, and divide 60.
Hmm. 15?
Yeah, or 3 or 5.
Keeping it in the realm of order 4, because 4, 15's a 60.
Yeah.
That's important.
Well, let's look at the other ones. K3 is congruent to 1 mod 3, and
Okay.
K3 divides 60.
Does that again? That's a even one, isn't it?
Yeah, everything congruent. No, like 7 is congruent to 1 mod 3.
Oh yeah, of course. So it's,
But there aren't that many elements that, I mean, to divide 60, you have to be less than 60. So, and to be congruent to 1 mod 3, there's not too many of those numbers that do divide 60. I mean, we can quickly examine all the possible divisors of 60. 1, 2, 3, 4, 5. Then you start looking products up from 6, 12, 3 by 5 is 15,
10.
10, 2 by 5, keep going, 15,
20.
12, did I skip 12? Yeah, 12.
You've already put 12, Killian.
I've already, thank you.
Yeah.
Yeah, I've got 12. I've already had 15.
20.
I should have
20.
done this.
30.
And that's it.
That's them all. Yeah.
Which of those are congruent to 1 mod 3?
I think George said before 4.
One is, well, and 1. So K3 might be 1. It's obviously only one of these, but might be 1, might be 4. 0 mod 3, 0 mod 3, 0 mod 3,
10.
1 mod 3.
13,
20, let's count to 2 mod 3, 3 to 0. But maybe the 5. So K5 must be congruent to 1 modulo 5 and divide 60.
So 6. Oh, and 1, yeah.
Nothing else.
No.
So only 1 or 6. So I think this is the ones. Yeah. So the number K5 is either 1 or 6. Is either 1 or 6 C-log P sub. And we know that all C-log 5 subgroups are conjugate. That's from the second theorem. So if it was the case that there were only a single one, if K5 was equal to 1, then what you're saying is for every G in A5, the conjugate of G with this C-log P subgroup, what we call it, H. So let H be a C-log 5 subgroup. If there's only one of them, the second theorem says all of them are conjugate. So when you conjugate, you do get another one. But if there's only one of them, then that conjugate has to be itself. If there's only one of them for it to be. So you actually get that, i.e. H is normal in G. In A5. But previously, back in that chapter on normal subgroups, it was proven that A5 has no normal subgroups. So it can't be 1. A5 is simple. I.e. has no normals. So that's a proof that K5 can't be 1. So K5 has to be 6. So in that situation, we get exact knowledge about the number of C-log P subgroups. So it has 6 different subgroups of order 5. I've got a selection of them here, but thank you. I'll switch color.
I need one permanent. You might want to avoid that one.
No, I've hidden that one from myself.
He definitely did not write a board in permanent. That's right.
Oh, did you not?
No, didn't happen. You didn't have to go and find a mysterious bag full of like a million board wipes and cleansers and what that was.
No, Jan went and fetched it.
It was like this big, just board rubbers and fluids. And like, how many boards do you have to clean?
I think it's screen cleaner.
Oh,
Clean
right.
on your computer screen. We also get some powerful theorems. Right? I mean, the general product in classifying all groups is to just say how many groups are there, how many groups of this size are there, how many groups of that size are there. And we already know how many groups are there of order 101. What is it about 101 that allows us to immediately answer that question?
Prime.
Exactly. And how many groups are there of that size?
Well, would it be 2, itself and 1?
And that's how many divides.
Oh.
How many groups are there of that size?
That's a bit 1, wouldn't it?
Every group of prime order is cyclic.
Hmm.
If you look at any of its elements, its order must divide the order of the group. But prime, if it's a non-identity element, has order bigger than 1. So every element has order 100. Every non-identity element has order 101. So every element generates the group. Every non-identity generates the group. So if the group has order 101, it has to be a cyclic subgroup. And all cyclic subgroups are essentially isomorphic, or are isomorphic to one. They're all just modeled on Z 101. Yeah. So, okay, so that means the problem is solved if you know the group is size P prime. There's only one of them up to isomorphism. The next, if you're doing some kind of induction over all possible sizes, you probably don't start at n equal, I don't think there's any induction argument possible from groups that will go n equals 1, n equals 2, n equals 3. But there might be more sophisticated kind of induction across the integers. A more sophisticated kind of induction across the integers goes on the length of the prime factorization, the primes being the base case, numbers just being a single prime. The next, a next step up in complexity is numbers that are a product of 2 primes. Okay, so that's what this term is about. If we're dealing here with every group of order the product of 2 different primes, not one of order p squared. It's the same prime by itself. But every group of order pq, what we're going to do is show that all of these groups have to have a normal subgroup. And under certain conditions, we will know that there's only one isomorphism class of them, because under certain conditions, we'll find out that it's cyclic. Okay? So it gives us an awful lot of, quite a lot of information about such groups. Now, if it's of order p times q, we'll call p the smaller prime and q the larger one. One of them's got to be smaller. Okay? And it says, well, we now know, it claims, from the Sylow theory, it claims that we know it has a single subgroup of order q. And this subgroup is normal in G. So how do we argue with that? Well, the first Sylow theorem tells it has at least one subgroup H of order Q. Yeah, it's a Sylow Q subgroup. Yeah, Q subgroup of order Q. Order Q. And the number of different Sylow Q subgroups, well, they're all conjugate. Here, but really he's just talking about the number of them. The number of them that there are, it divides the order of G, which is PQ, and it's congruent to 1 modulo Q. So the possibilities for the number of them that there are is 1. And the next number that's congruent to 1 mod Q is Q plus 1. The next number that's congruent to Q is 2Q plus 1. Right? There's one of those options. But the third theorem also tells us the number of them that there are also divides the order of the group. Right? But you see, it can't be any of the options Q plus 1 or 2Q plus 1 or 3Q plus 1, because all of those are too big to be a divisor of the size of G. Right? Because the size of G is P times Q. So they're all, so 1 plus Q is already too large to divide the order of the group. Hence, there's only one. Okay? H can only be conjugate to itself. There's only one Sylow, and so just like in this little proof by contradiction, if there's only one of the, if there's only one Sylow Q subgroup, it must be self-conjugate under conjugation by any other element. So that means it must be normal. So this must be a normal subgroup of G. So we know that G cannot be simple. So if your group has order a product of 2 distinct primes, it is not a simple group. So it has a normal group, so it is possible to simplify it by a factor operation. Yeah, now the other piece of information was look at the Sylow P subgroups. Okay, so there's at least one of those. Okay. Again, the number of them must be congruent to 1 mod P. So it must be these. And it must divide the size of G Yeah, so little, he's skipping details there. I'll show it to you. So K, the size, the number of Sylow P subgroups. Call it, I was about to call it K subscript P, that would be terribly confusing. Let's just call it N. All right. The two things is N must be congruent to 1 mod Q, sorry, 1 mod P. So in other words, N must be some multiple of P plus a 1. And it must divide, well, Sylow's theorem says it must divide G, size of G, i.e. N must divide P times Q. But now, if we already know that N is congruent to 1 mod P, what's the greatest common divisor of N and P? So if it's co-prime to P, this was called Euclid's lemma back in number theory. If N divides this product and N is co-prime to one of the factors, so it shares no common factors between N and P, but N somehow still divides the product, that means all the factors of N must be contained in Q. So in particular, or in fact, get an even stronger statement, N must divide Q. So N must divide Q. So that's he just leaps straight away to that. But there's a little justification step there. So it relies on this fact that the GCD of N and P is 1. So either, yeah, and Q is a prime number. So there's only two possibilities for N, 1 or Q. Yeah, 1 or Q. So either, so this is N, 1 plus Kp, it's either equal to Q or 1 plus Kp is equal to 1. If N is equal to 1, yeah. See, the extra condition, the statement, the theorem was that Q is not congruent to 1. So this case, modulo P. This case here is where Q would be congruent to 1 mod P. Okay? So if we're arming ourselves with this assumption, we're assuming that that's not the case. So it must be this possible. Right? So it must be that possible. So then we're just saying N is equal to 1. So we're saying if Q is not congruent to 1 mod P, then N is equal to 1. So i.e. K is normal in G. If there's only one Sylow P subgroup, second theorem says, oh, Sylow P subgroups are conjugate. That means you conjugate that by something, you get another Sylow P subgroup. But we've just said there's only one. So when you conjugate that, you must get itself all the time. All the time meaning for any choice of element from G. So that it's normal in G. K is normal in G. We already proved the H subgroup was normal. So now we have these two normal subgroups. H and K, both of them normal in G. And he claims we can easily show G satisfies the criteria given in chapter 9 for the internal direct product of H and K. So why is that the case? First of all, we had to have it. So what were those conditions for existing internal direct product? Look them up.
They're only intersectors, yeah, don't they?
Exactly. Brilliant. So trivial intersection. Why is that true? And that's a condition it has to have, but why is it true? Order of H is Q, order of K is P.
If you were to direct product and then there was an intersection, the size of the composite group would be wrong.
Yeah, but that's assuming the direct product of them is group. Well, that's what we're trying to prove. So you're assuming the result there. But you see, they're each of different prime order. But every non-identity element in H has order Q generated. Every non-identity element in K has order P. So if something is not the identity but is in the intersection, what you're saying is it has order P, and then after that you're saying it has order Q. Well, that's contradictory. You can't have two different orders an element. So the only element that can possibly be in it is the identity, which is order P is 1, which is P to the 0, and order 1, which is Q to the 0. The only time powers of P and Q coincide. Trivial power. So that's okay. That's true since the order of H is Q and the order of K is P. Camera focused on it. The other condition I think we had to have was that H and K
Was isomorphic to G.
Yeah, that H times K was equal to G. Are you looking at the conditions there?
It's stated in the book that G is equal to HK, which is equal to a product of two elements, little h, little k, where little h belongs to capital H and K belongs to capital K.
I think we will get that in a moment by considering the orders. But the second thing, we have to know that they commuted, didn't we?
Yeah, HK is equal to KH.
So for every little h and k coming from the appropriate thing, little hk have to equal k times h. Have we proved that? They had to commute on the element level, didn't they? Yeah. Yeah. You see, we'll get that first condition once we know, if we can prove that, then the internal direct product is a subgroup of G, but it'll be a subgroup of G having size P times Q. So therefore it has to be all of G because it's the same size of G. But we need to prove that commuting bit. Now that's equivalent to saying HK, H inverse is equal to K. And we know HK, H inverse, it's a conjugate of an element from K. K is normal, so we know at least that this must be an element of K. Is it equal to little k that it was that you began with? I hate it when they say this. They say, "Oh, we can easily show." Well, it's easy when you know how, but
It was theorem 91. Oh, if the GCD of the two elements is also congruent to, is equal to 1 by theorem 9.21, which states there, the group Zm times Zn, the direct product is Z times M.
yeah.
Zm, and even though
Yeah.
the GCD is that.
Yeah, I mean, we know H is isomorphic to ZQ. K is isomorphic to ZP. Is there a result about
Inverses.
the properties that normal subgroups have when they have trivial intersection? I think we look back and we might find a result about normal subgroups that when they have trivial intersection, that their elements actually commute with one another. I think we might find that if we look back on normal subgroups. But I think we'll have to settle that on Friday. I think we're out of time. ODEs are coming in here. ODEs coming in.
PDs.
PDs.
Okay?
I don't.